Okay, so I think we're gonna start. So welcome everybody to this event. So my name is Lourdes Agapito, and I'm a professor of 3D computer vision. And I'm going to be the first one to talk today. And I'm going to be talking mostly about our masters in computer graphics, vision and imaging, CGVI. So I know that some of you are former students from this program, some of you are current students in the program, and some of you hopefully will be maybe future students in the program. Maybe some of you might be interested in doing this program. It also, talks a little bit about our research, although Dan Stoyanov, who's talking right at the end, he'll be talking more about the research that we do in the group. So we're very lucky to have two great speakers from industry today, from Framestore and from the Foundry. So I'll introduce them afterwards. I'm incredibly grateful to Kate and John for being here to talk about all the amazing things that you can do in VR and computer graphics and computer vision in industry. I think it's very, very exciting times for computer graphics right now. So this is what we say in our webpage, what the CGVI in computer graphics and vision and imaging is about. So these are all the areas that we cover. So it's super long to talk about this. But basically, so the people who actually teach in this program, we belong mainly to two research groups. So one of the research groups is the computer graphics and virtual environments group, and the other one is the computer vision and imaging, so the vision and imaging sciences group. So we cover really, there are three main aspects that we cover in this program. One of them is computer vision, the other one would be imaging or maybe low-level vision and image processing, and the other one is computer graphics. And we also cover virtual reality and virtual environments. So those are all kind of examples of some of the topics that we cover. But really, the main thing about this is that there are amazing people at UCL working in all of these areas. So these are my colleagues who work in graphics and vision and imaging. So you'll see some of the people here, actually people who are working in medical imaging. They're part of the Center for Medical Imaging, CMIC. So Simon Arridge, for instance, is the director of the Vision Group, and he's also the director of the Center for Inverse Problems. And Danny Alexander also works in medical imaging. Anthony Steed, Professor Anthony Steed, is the head of the graphics group. So you'll see that we focus on all these different areas. So all of these are internationally leading researchers, and we kind of do research in very exciting areas in vision and graphics. So I'm just going to talk about the modules that we have in the course. So we have 4 core modules that all the students do, and these modules are the ones that you see here. So image processing, computer graphics, research methods and reading, and MMAI, mathematical methods. So these are modules that cover all the fundamentals in computer graphics, in image processing, fundamental methods in mathematical methods and tools that we need to do imaging or computer graphics. We also have this very nice module in research methods and reading, where the students actually do all the background research for their final projects. And they also learn how to read a research paper, how to present a research paper to their colleagues, how to actually write up a research paper. So they learn kind of core skills about research, how to do research. So in image processing, I teach this course, and we focus a lot on low-level vision. So, for instance, we do noise reduction in images and image denoising. We also look at the Fourier transform. We look at how to extract image features and lots of other topics. And these are all the optional modules that we have. So between all these optional modules, the students choose 4. There are very advanced modules that we offer. So we offer modules in module in biomedical imaging, inverse problems in imaging, which is an incredible course in optimization, how to optimize and how to model inverse problems and how to optimize them. There's also a course in machine vision, which is incredibly popular with not just the students in our master's course, but also in the machine learning course. So this is a super popular course that many students do. So it really is about how to use machine learning approaches to solve computer vision problems, how to do recognition, how to do detection of objects. So a very interesting course. We also have a course in geometry of images, so for instance looking at scale space. We have a course in virtual environments, and one of the amazing resources that we have here at UCL is that we have a cave, which some of you might be able to go and have a look at afterwards. So, you know, the students actually program and they code their own applications that can run on the cave, and they can do really quite cool things as part of the course. We have a fairly new course in acquisition and processing of 3D geometry taught by Nilo Mitra. This is a very popular course. It's kind of based on a course that came from Stanford University. So they look at how to acquire 3D point clouds and also how to process the geometry. And they do very cool projects at the end of these courses. Computational photography and capture. So one of the projects that the students have done this year is to actually build a structured light system to capture 3D geometry. So, you know, it's pretty hands-on, and they do very kind of interesting courseworks and very interesting projects. And then, of course, at the end, all the students do a project. They do a project over the summer, so they have 4 months to do the project over the summer. They submit it in September, and we have something that's very nice. We all gather here, and all the students do a presentation of their project. So we have a really exciting day at the beginning of September where we have all the presentations, and everybody in the group attends, and it's a really great day and a celebration of everything that the students have done. So I'm just going to showcase a couple of the projects that some of our students did last year. So this is Stefan's project. He's actually sitting here with us, and so he actually did a simulation of the tissue. In this case, he was simulating a liver, the tissue of a liver, and modeling things that are very complex, things such as elasticity, spatially varying materials. Hello. You're all late. Yes. Oh God. Okay, so Stefan did an amazing project here. You see some of the images of the simulations of the liver, and of course the nice thing is that this can be applied to medical imaging, and this was the motivation for this project. Dan Stoyanov was the supervisor, and he works in surgical robotics. He'll tell you all about it later. So that was the main motivation. But of course, you know, this can also be applied to computer games and to other areas. So I'm just going to show you this great video that Stefan prepared for us. So here you have a simulation. The amazing thing is that this works in real time and takes advantage of GPU processing. So these are the kinds of simulations of tissue that Stefan was actually able to model. So here you have another nice simulation of spatially varying properties of tissues. And Stefan decided to stay on at UCL and to do a PhD. So he's now a PhD student with us, working with Gabriel Broster, who's sitting just here. And he's funded jointly by UCL and by Microsoft Research, and he's working on, you know, very exciting things about how to model the way that animals walk, so quadrupeds and mice, tracking mice and modeling that in 3D. So, you know, this is a very nice story of projects that lead to students doing very exciting research afterwards. So this is another example of a nice project last year. So this is Ki Liu, who did his project under my supervision, and we were looking at, so what Ki did was to start off with just a video sequence, a plain video sequence, and to reconstruct the dynamic shape in 3D. So we have just a single camera. How can we actually acquire a 3D surface of this deformable shape that's varying over time? Of course, this has applications in VR, in virtual reality, in augmented reality, in animation. And you can see here, this is a comparison with a previous method in the middle, and on the right you can see, very, very vivid reconstructions where you can see that just from the video, no depth cameras here, were able to recover even the wrinkles of the face and very, very high frequency details on the surface. And also Ki was, he decided to stay on and do a PhD. He also got one of these Microsoft funded scholarships. So, this is very nice. So now we actually have quite a few students who are partly funded by industry who are doing research and PhDs in our group. So these are two of the projects that the students carried out last year. But I also wanted to talk a little bit about former CGVI students. So, people who've actually done this degree and who've then gone on to industry. So a lot of the students have stayed on to do PhDs, but not all of them. A lot of them have also gone to industry. So, for instance, Frederick Bess, after his PhD, he went to work with John at the Foundry for a while, for a few years, and now is working in Google DeepMind. So obviously John will tell us all about what they do at the Foundry in a moment. Another student, so Jonathan finished in 2014. He now works at this really nice startup in Paris, where what they're doing is they're kind of using drones to take images and footage of archaeological sites or just areas that they want to, heritage that are important for cultural heritage. And they take video footage and they want to really reconstruct and render these with maximum, just very, very, very vivid reconstructions. So here you can see an example of, I've forgotten where this place is. I think it's in Syria. So for instance, they're very concerned at the moment about some of the sites in Syria that are being destroyed, and they want to really acquire footage and reconstruct very, very vividly and have very, very accurate 3D models to preserve human heritage. So you see the detail of the 3D models that they're acquiring. So Jonathan did his master's, CGVI master's, and straight after his master's he started working for this company. It's a startup that's based in Paris, and so took me back. So other students who've worked with us are Guillaume Boisset, who's now working at Sony. And he's developing sort of games for PlayStation. Audrey Fontanet also finished last year, and she's working on augmented reality projects in Thalys in France as well. So you can see that there's a very broad range of projects and applications that our students are actually going on to work on. So this is really where I wanted to finish. So I just really wanted to give people, I think some of you who are here are actually prospective students of this master's, and really tell you, come and do a master's with us, come and do research with us, and you'll be able to go on and do really exciting jobs or exciting research afterwards. So next, I think Kate is going to talk to us. Kate is actually a research engineer at Framestore, and you did this program a few years ago. So thank you. do, but it's always a little bit tricky. Let's try it first. Just in case. Do you have to set up the sound? Is it this one?
Sorry, almost. So this end goes to you,
Okay.
and this end goes here. And the water goes lower. And that may or may not be enough. There's a volume from here, but I think it's turned all the way up.
Okay, I'll just try.
Are we able to check?
Coming out of my machine, I think.
Are you in the headphones or speaker?
That's better. Cool. Okay, good to go. Okay, so yeah, my name's Kate Burgell. I'm currently a senior R&D developer at Framestore, and as Lauda said, I was a student here about 10.5 years ago on the MSc Vision Imaging and Virtual Environments course, which was a predecessor to the current CGVI course. So I'm going to tell you a little bit about the work I've been doing recently at Framestore, and kind of try and apply the knowledge I gained on my MSc to that. First of all, I'll just give you a brief history of how I got to where I am. So I did my undergraduate degree at University of York, after which I spent a year working at Moving Pitch Company, which is another VFX company down the road, and then I decided I'd rather be sitting at a desk than crawling around under it. So after talking to some of the managers there at MPC, we decided that pursuing a master's course here at UCL was a good way to deepen my understanding of some of the principles that I would need for going on to a research role. So since then I went back to MPC. I also spent a few months working at Electronic Arts, which was a job I got through the contacts with this department and the company there. And I've also been lucky enough to spend 18 months working at Pixar in California as a research assistant. And that's a role I definitely would not have been able to do had I not studied here, because one of their key requirements was to have some experience on a research project, and so the 6-month project I did here, excuse me, fulfilled that requirement. So I've worked on quite a variety of different projects since studying here. I'm going to talk to you really just about the ones that are going on at Framestore, because those are the ones I've got the pictures for. So first of all, I'll introduce Framestore. It's a company that's about just over 30 years old. Mostly works on feature films, but there's also a commercials department, a virtual reality team, and other various projects. It's made up of people from a mixture of backgrounds. We've got creative people with backgrounds in art, architecture, design, as well as the more technical maths, science, physics, computer science roles. And there's a little show reel that shows some of the work we've done.
So there's a selection of some of the finished work that Framestore completed recently. There's quite a variety of different applications and areas that we're working. I'm going to talk just about the feature film side because that's the one I know best. And before I go on to what I actually do, I'm just going to give a quick overview of how the company as a whole produced those finished images, just to put things into context a little. So Framestore's work actually often starts before shooting begins on the film. We have a concept art department who will draw out, design how characters, environments, what have you, are going to look. And then once we do get the live action footage from the clients, there's various preparatory stages, such as tracking to add markers to the filmed footage, pick things out just so that we'll then be able to combine the CG elements with it later on. So the CG elements, before we can animate them, we have to create them. We've got various departments who generate the CG objects that we need. So modelling they sculpt the 3D geometries for the characters or the props or basically anything that wasn't on the live set. Groom create the hairstyles for the characters, textures, basically colour in the models and determine how they're going to look on the surface. Matte painting create backdrops and various other things that go into the scene. So we've got our building blocks for a CG scene. And the next thing we need to do is actually make them move around, make them act. Characters go through a process called rigging, which is basically giving them a skeleton and defining joints and how they move. And adding controls that allow the animators to then pose the characters and make them act. We also have a crowd department who are sort of automated animation for when you have vast numbers of characters in a scene. You don't want to have to animate them all individually by hand, so they use artificial intelligence and some predefined animation loops just to create those large scenes. And then for things that aren't characters, just the general props and whatnot, we have the effects department, and they deal with physical simulation, things like explosions, particles, fluids. And the creature effects departments also deal with simulations of things that are related to the characters, so things like hair, cloth and skin. So by the time they're all done, we've got all our objects in the scene moving around where we want them to be. But they're all still kind of grey, and we need to figure out how we want them to look on the finished film. So we have the look department who determine how the final shots are going to look, so the camera angles, the viewing points and that kind of thing. And then the lighting department, they're the ones who are responsible for assigning textures and shading and colours to the objects, and also for positioning the lights in the scene to get the maximum effect out of it. And so now we've got all our CG elements looking how we want them. The final stage is to put it back with the live action footage, combine it all together in a way that's as seamless as possible, and that's where the compositing department come in, and then they will then produce the final rendered output. So that was a very, very quick overview. There's a little show reel that shows a breakdown of some of the scenes from Gravity. So hopefully you could see some of the little building blocks that went into making the scenes. Okay, so now back to me. And where does software development come in? Well, basically our role is to support all of the, well, as many as we can of the departments I've just talked about, to make their lives hopefully easier by automating as many of the kind of boring processes as possible. So instead of having to set the position of every single object on every single frame, we can figure some of that out just based on physics or what have you, and let them concentrate on really nailing the key components of the scene. So this is particularly effective on things that involve a lot of simulation, where we can set up a load of equations or rules, put in some initial values, and just let the computers figure it out. So yeah, the departments that I've myself been working with are effects, creature effects. Crowd is an AI simulation rather than the physics one, but a similar kind of principle applies. So related to R&D, which is the department I'm in, we have a shaders department too, and they deal with also with physics, but this is the physics of light, so using equations that determine how different materials affect the light, how they transmit it, refract it, and so on. That will then get plugged into the renderer, and that determines how the simulated rays of light get bounced around the scene and end up back at the camera to produce the final image. So they're a really crucial component of producing the finished look. And it'd be remiss of me not to mention our other software developers. These aren't particularly graphics-focused roles, but they are essential. Pipeline are in charge of looking after the assets. We have a lot of data, as you might imagine, so many models and textures and everything. And so making sure that everybody in the company has the right version at the right time is pretty crucial. And then, like any other company, we've got various databases and scheduling software and things that people also need to support. Okay, so I'm going to look at some of the actual projects we work on now. So things I've worked on myself. One of them was the formation tool, which is for importing simulated output from a third-party tool, Massive, which was the crowd simulator written by Weta and used on their Lord of the Rings armies simulation. And the role of that was to import the simulated data into our own tool. We use Maya for most of the animation pipeline for the modelling and animation and all that. So we wanted to be able to get the output from Massive and put it in a way that would fit with all the other components that are created elsewhere and work with our rendering. Although a lot of this wasn't actually graphics-centric, there was some sort of fairly generic software engineering principles required, just sort of file parsing and data storage. Obviously the results are visual and we need to be able to see what's going on. So we had to be able to take the joint transformations that were stored in the file and understand the scene hierarchy and apply the joint positions to the geometry, the character meshes, and make sure that we can view them. And there's this kind of, a lot of the thing with writing tools is making it easy for the artists to use. So we had like these little guys in the corner are just a skeleton representation, so they can get a preview of the scene without having to deform the geometry at every stage and just do lots of checks and edits and quick updates. So there's quite a lot of graphics in that. And then this little demo scene shows another preview of just the geometry models being deformed to match various joint positions. And we also had to deal with things like being able to edit it. So if you want to just change the animation of a particular character, you can see these little dancing guys at the front. They've had an overridden animation applied. But we don't want to have to go and resim the entire crowd. It could be like thousands and thousands of people and take a long time. So applying extra transformations on top of those that was part of the requirements of this project. And so again, that's lots and lots and lots of matrices and 3D transformations and linear algebra. That kind of comes into everything we do. So here's just a brief finished project. I don't know how well you could see that through all the bats and everything. But yeah, there was actually an army down there, and it was sort of standing around, and it actually had some physics applied to it as well as the artificial intelligence, the AI. Do you want me to play that again so you can see it? Next one. Okay, so hopefully you could see there was some army in there. We've got lights again now. Thank you. So yeah, so that was one or two. So yeah, my next project, I guess at least one person in here will be familiar with the concepts. It's same as Flab, and it was a finite element simulation tool for, hello? Thank you. Yeah, finite element tool for simulating deformable objects. Yeah, up until relatively recently, most simulation in VFX was done using rigid body dynamics. So you take an object, you assume its shape stays fixed, and you just move its transformation in space, which is fine, but it's not particularly realistic because in real life things squash and bend and stretch and what have you, and we want things to look as realistic as possible. So finite elements, for those who don't know, it's a technique that's been around in engineering for quite some time, but recently computational power has increased to the point that we're actually able to put those equations and use them in a fairly interactive way. So it works by splitting an object into lots of elements. So this cube split into a lot of tetrahedra, and we compute the forces on each element using equations for the stress and the strain, and then we put those into big equations based on the force equilibrium rules and solve for the whole object. So again, it's not, I wouldn't say it's so much graphics heavy. Again, we need to see what we're doing, so we have to draw the things, but it is quite physics heavy, and it does use a lot of the same core concepts in maths and yeah, just equation solving that come up in graphics kind of across the spectrum. So again, lots and lots of matrix, some really, really big matrices, calculus, constraint optimization problems, and that kind of thing. So we have some little videos showing it in action. Some gummy bears, and these are just some test scenes for the collisions we've done recently. And Flab was used on the Paddington movie just to create the wobbly bear bellies, giving a bit more motion. So that's, yeah, Uncle Pastuzo. And there he is in the finished film. And it just gives the characters a bit more life and a bit more flesh, literally. So those are the things I've mostly been working on at Framestore in the past couple of years. It's a team of about 15 developers, and we have at least 20 odd different tools, so across all different departments that use them. So there's a few other things going on. My favourites, we have Flush, which is a fluid solver. That's another big physics solver, kind of similar to Flab, lots of matrices and figuring stuff out. Here's a quick demo showing some nice little wave effects. We also do have F-Bounce, which is quite an old tool now. That's another one I wrote quite a while ago. It's the rigid body simulation I mentioned earlier. Although it's not quite as fashionable as finite elements, it is still very useful. If you've got a lot of objects, it's much, much quicker to just solve them as a single entity rather than compute the force across them. And if you've got things like bricks and debris, it doesn't tend to squash around that much, so that's fine. We also have a grooming tool called hair filters, which uses curves to represent hairs. So there's a very real application of I think they're beast lines or whatever you use for those. So we take a set of lines represented by a series of points and apply various transformations to those to create various different effects. So things like just jittering them a little to create kind of scraggly hair, or changing the length, or various other properties like that. And there's also a little bit of physics involved, I think. So they also have a brush tool that allows you to kind of pass something over and just affect it like that. And there also some physics simulation comes into that, because you have to take into account the fact that you might style a beautiful kind of Mohican or something, but as soon as you put it into a simulator, it's just going to collapse. So you have to take into account that it has to be working against gravity. So there's that kind of thing involved. Speaking of which, we have the related tool, which is Dynamo, which is another physics simulation tool, but this time based around the curves that represent the hair. So as a quick demonstration of Aslan, and his mane is reacting to Aslan's movement as well as the contact with the other character. So those are some of the R&D projects. There's also research projects going on elsewhere in the company. Motion capture is a technique that's been around for quite a while. That's basically capturing the movements of an actor with ping pong balls, turning that into a set of animated joint transforms that can then be applied to a computer-generated character. So that's been around for a while, but lately the focus has been on doing it real time. So you can actually see the digital character moving as the actor is performing the motions on set. So here we're actually looking at a laptop screen on set with the real actors just behind it. So that just gives the director the opportunity to see how things are going to look as it's being filmed. Yeah. Very elegant. And there's a video of a similar kind of idea being applied to facial motion capture. So it's actually using the features of the face instead of like ping pong balls or markers to pick up the motions and then transfer those via this intermediate model in the bottom left corner onto the finished character. Okay, so another department in Framestore is the virtual reality studio, and they've worked for about 18, I think, different clients, creating immersive experiences, mostly the sort of advertising thing, also for exhibitions. There was a Game of Thrones travelling exhibition recently, and they did an installation that allowed you to go up on the wall, for those who know what it is, and kind of be shot at by wildlings and get kind of vertigo from looking on the edge, and it looks kind of cool. So I have another video that shows that. Can we get the lights again, please? Thank you. the lights back, please. Thank you. You sat in the wrong place today. Okay, so that's a very, very brief overview of some of the things that go on at Framestore and at similar VFX houses. If you are interested in finding out more about VFX, then Framestore has various online presences. It's got social media accounts and also a website where they regularly post articles about work that's been done recently. For the VFX industry as a whole, there's a few online magazines. VFX World is good. Cinefx produce a fairly expensive printed magazine every couple of months, but they also have quite an interesting blog, including an ABC that talks about various different aspects. So those are kind of general interest resources to look at. I know some of you here will probably be thinking about kind of future career paths. So if you think that VFX is something you would like to work in, things we look for first and foremost are just being a good coder. A strong software engineering background is always an asset. And so by good coder, I don't mean sort of knowing all the fancy little shortcuts and how to make things kind of super fast, but in a way that no one else can understand. As I mentioned, we have more tools, more projects than there are coders, which means that sometimes projects have to be kind of let be for a while, so if they can keep running without breaking, that's always a really good thing. It also means that you're quite likely to inherit and work on someone else's code. And depending on how much you like your colleagues or want them to like you, it's always best to write code that is clear, legible, maintainable, commented, that kind of thing. So that's definitely an asset. Obviously, understanding the basics, graphics principles is always an advantage too. Though, as I mentioned, a lot of the tools we write don't use those directly, so they're kind of a useful thing. Yeah, LinkedIn profile's always good. If you write it as you go along, it kind of helps you remember what's going on. We do use it in VFX to seek people out and also to check up and see what they've done and who they know. It's always good. And then just knowing about some of the tools we use is handy. So mostly we use Maya for all the 3D aspects, the modelling animation. I mean, as a programmer, mostly what we tend to create are spheres, because if it works on a sphere, it's going to work on anything. But just having a rough idea of the interface and what goes on with them is always useful. Most of the software providers allow free access for students at least. So Autodesk have free all their software for students, I think. Another one we use is Nuke, and I think, well, the next speaker will be able to tell you more about that one. And then there's also video tutorials that you can use just to get an idea of how things work. So that's basically all I had to say. I hope you found it interesting. I don't know if we've got time for any questions, or yes, maybe.
Can I ask a question? You're talking about the skills people need for roles at Framestore. What's your interview process like? You've got to be able to code. Do people walk in and get coding tests?
We tend not to give coding tests, actually. It's a fairly informal process. We kind of look at any projects people have done in university, and if you've got examples of things you've worked on, obviously there'll be some kind of questions on coding just to make sure that you do know what you're talking about. We don't go in for formal kind of written tests, because it is quite hard to write down code, I find, but as long as you can demonstrate that knowledge, then often if people have websites with working examples or something, that's quite handy.
So the MSc project's quite critical.
Yeah, that would be a really useful thing to have, definitely.
Do you work in London?
Yeah, just down the road. So.
How do you think the VR has changed since you did your master's 10 years ago? Like in terms of shift-wise, because it's such a fast-moving industry, it seems.
Well, the VR haven't had a huge involvement in, but VFX has changed. I think the biggest change is things like the finite elements and the simulation processes. I mean, it's like anything else, it's down to computational power. So whereas in the past a lot of VFX was about fudging things, basically, it's like how can we make it look like it's doing the right thing but without actually having to do all the solves. Nowadays it's more about this is what actually happens, or how we model it mathematically in engineering in the real world, and putting those equations into the computer and just trying to make it realistic by doing it realistically rather than kind of fudging it.
Is your instruction pipeline FEM like Kali and MPC at the moment, or are you still on the rigid body side?
We're still on the rigid body. We use that for, Gravity was all rigid bodies and things like that. We are, Flab is a kind of our initial investigation into finite elements, and so it's been used on a couple of little things, but having the technology and getting people to use it isn't always, yeah.
Thank you.
Do you, I saw in a lot of the stuff that you do, you use optical tracking systems, and there's also robots, and there's like kind of loads of technology and hardware being used as well.
Yeah.
Maybe not for the simulation side,
yeah,
but
yeah.
for other aspects. Is that an advantage if students during their project have exposure to various kind of platforms that exist?
Depends exactly what you want to do. In R&D, we're all just virtual stuff. The more experience you have I guess anything that involves 3D transformations is basically what we're all about. But yeah, there are other development roles at Framestore that come in for kind of, some of the robots I think in the video were for Gravity, and there they actually, because of the way they wanted to do the shots, the existing cameras weren't kind of manoeuvrable enough to get the angles they wanted, so they ended up taking a car manufacturing robot and adapting that so that they could do that. I'm not entirely sure who did that or where or why, but I'm pretty sure there must have been some software people there. And they also have, one I didn't mention, there's a team that do, there's labs who do kind of installations, so they've done data visualization for the stock exchange, and they do installations. I think in the first videos there's did an exhibition for Valentino at Somerset House, and there's a rose with kind of projected patterns onto it, and they had to do kind of custom software to be able to project from 2 cameras without the shape of the paper flower getting in the way and distorting things and shadowing. So there's definitely a variety of roles.
So you mentioned motion capture using markers, but you also showed some examples of facial capture without markers.
Yes.
So how much effort is there put into markerless capture at the moment?
I think that's definitely where people see the future, because having to mark actors, it takes ages to put the dots on the actors, and it can be quite distracting for other ones interacting or them interacting if they've got kind of dots all over the face. So, the less preparation they have to put the actors through, the better, really, and just
Just to say thank you for mentioning the non-lab end of CG because I liked that for a while.
Oh yeah.
While I was doing it, I got the impression that people were bringing more things like writing rigs that were pre-built that you then just rendered against, so that there was less matching of the lighter had to do less matching between the shot in the footage and the colours that he was doing.
Yeah.
So I just wondered now, is that more automated now, or do they still do a lot of it by eye?
There's a lot by eye, I think. For something like lighting, it's all about the kind of the end visual effect. So there's obviously, lighting is not something I've worked with myself much. They do definitely set up rigs. I think one thing that's quite good is often the studios are willing to get the VFX company involved before they start shooting, so they can try and set up the set in a way that will be consistent with our own virtual set and kind of get all the lights in the right place and make things match. So, yeah, obviously we want to automate as much as possible. There's always going to be final tweaks to sort things out.
Well, thank you very much. That was a great research at the Foundry, another VFX company based in London. I think we're lucky in London to have all these amazing companies doing VFX. So John did his PhD at the University of Surrey with Adrian Hilton on motion capture, I think, or markerless capture.
Markerless capture of realistic models of people.
That's right.
No skeletons, just surfaces.
And you've been at the Foundry for quite a while, right? So thanks a lot for coming as well and for telling us about your research at the Foundry.
Sure. Okay. Yes, hello. I'm Jonathan Stark. And if you haven't heard about the Foundry before, we produce software tools for the creative industries. So we produce modeling tools, texturing, painting, animation, video editing. So this talk, well, so I'm head of the R&D group, and we do pretty much 2D and video processing, so visual computing tools. So I'm going to tell you a little bit about the 2D side of the film industry, which kind of leads in quite well from the 3D side we just heard about. So this is really, it's quite an old shot now, showing my age a little bit. In fact, I'm not sure if anyone really recognises this movie. It's The Mummy 3 from about 8 years ago. And this was my introduction to the world of film. And just play it through. I don't know how well you can see on this screen. You get the halfway house? I think we're okay. Okay, so this shot, you're looking at two shots. So the centre of the screen, you're seeing a cleaned up version of the plate that came from set. And bottom right in set, you're seeing the final version of the shot that was created in post, we say, in post-production. And so the problem here is to convert Jet Li from normal Jet Li into a mud monster at the end of the shot. So you would think that's kind of a simple process to go through. You need to produce a 3D model of a mud guy and a 3D sim of the mud pouring out of all of his body. You slap the two on top of each other, do a bit of grading, lighting, and away you go. And it turns out it's not actually as simple as that. So there's different stages you have to go through to compose this final shot. So for example, just to do the overlay of the CG model onto the original footage, you actually have to cut out Jet Li from that original footage to begin with. That's a process that we call clean plate generation. So an artist will get a shot from sets, comes into post-production, and they will work carefully through that shot to in-paint the background over the top of the performing artist. And they do that not just as a 2D process, they might do some paint work, but they do it as a 3D process. So they'll go into the scene and they'll build up projection surfaces. So background planes, tabletops, things like that that they project the original footage onto, kind of behind the actor to remove him. So you go through a process of clean plate, and when you have a clean plate, then you can drop in your CG model and your simulation. And what struck me about this shot, is why it stuck with me so long, is that the director came along and said, well, I like the beginning of the performance, but I really don't like the end of it. So we want to change the performance completely. So to do that in movies today, you actually have to go through the process of creating a digital double, which is very expensive. You need a lot of modelling, you need to scan the actor, you need to rig the whole of that digital model, then you need to recreate that performance. So it's a very, very technically challenging and also a very, very expensive process. But to change the performance in this shot, what they effectively did was the 2D artists rigged the video so that they could reanimate the performance in the video itself. So as a 2D process, the artist came in, picked particular key points in the shot. Can't get it on my slides. Here we go. They tracked in a rough geometry for the face, picked out the key expression points as blend targets to reanimate the expressions of the face. They built out simple primitives, cylindrical primitives for the arms and the chest plate so that they could reanimate that from the live action performance into the CG mud model. And effectively they could recreate and reanimate the performances in 2D. And when you look at the final plate down on the bottom right, actually the only thing that's real at the end of the day is from the legs downwards. Basically the waist of the body and the legs came from the original footage shot on set. Everything else that you see in that bottom right final clip is recreated completely, just as a 2D process integrating a 3D simulation that came from Maya, presumably. So I was really quite surprised when I moved to the movie industry that it's not just all about the beautiful physical modelling and 3D simulations. There's actually a lot of work that happens in 2D departments. And those 2D guys, they need video editing tools to assist them with that process. So this is a snapshot of what makes up a film production pipeline. And Kate already gave a really nice run through of the different stages in producing a film. She concentrated mostly in that post-production phase. But there's a hell of a lot that goes on. And this diagram is really just to show you the yellow box where I'm talking about, but also to give you kind of an overview of how films are made. It kind of starts out in pre-production, you create your story, you do your shot planning, you go on set in production, you shoot your footage, then you take that footage from set and you go into the post-production industry, where you assemble all that data and it gets combined and integrated to create the final shots that are edited together to make the movie. And this is the reason why movies cost so much, is because there's so many people and there's so many things to deal with, there's so many companies. And for me, as a vision researcher, the interesting thing here is all the data that you get coming in that you have to deal with. So you've got 3D data sets from LiDAR scanning from sets that you have coming in. You have digital photography. You might take many stills on set to build up photochrometric models, or you might use those stills for texture references for building assets. You've got principal photography coming from set, so that's the main camera. You've also got witness cameras coming from set to give you frames of reference for the shoots. And all these things have to come together. And as Kate was saying, these things tend to come together to deliver the final shots at the compositing stage, the video editing stage. So we think a lot about how do you deal with lots of data, how do you manage it? We also think about the data processing, how do you simplify the data processing, and how do you do data processing that enable artists just to focus on the creative process that they want to get to. So they're not bogged down in creating data points, if you like. They can just be creative and manipulate video in the way that they want. So our job is all about making artists' life easier. And this is a picture of our tool called Nuke, which provides an image processing pipeline. And this is pretty much the industry standard way of dealing with video in the film industry. So you might be more familiar with tools like Adobe After Effects. That's a layer-based way of dealing with video, where you bake down layers and modify the footage. In this world, we have a node-based procedural way of manipulating input footage that comes captured from on set for the film. And it's really key that it works this way, because everything you do to footage has to be reproducible. A 2D department might have hundreds of artists. There might be tens or even hundreds of artists at any one time working on different iterations on a shot. They all have to be able to work from the original footage and recreate all of the image processing that they each did on a shot to be able to review, modify, and iterate. So the fact that these pipelines are procedural is really key. They have to be reproducible. Every bit of image processing that you do has to be completely deterministic. So one artist working on one machine with NVIDIA GPUs might want to send some stuff to another artist working on ATI. They might want to take the shot and the result they're working on and send it off to a render farm, which has got hundreds of render nodes working on CPUs. All of this image processing has to be consistent and produce exactly the same result wherever it's processed. And the algorithms themselves have to be scalable. You need to be able to distribute the work that you're doing to many computers for processing, so you can't have sequential processing. So there's lots of constraints on the type of image processing algorithms we create. And when we create an algorithm, they tend to work as a node of a processing block that sits in a big recipe that a technical artist produces to create a final visual effect. My voice is going. So this slide just gives you a snapshot of some of the tools that we create for artists working in an application like Nuke. And these are very much classic computer vision algorithmic tools. So we've got, top left, image denoising. So you take your film footage, it's covered in noise, you take that noise out to integrate your beautifully rendered CG elements. You then need to regrain it to look more like original footage again. So you're dealing with single frame, multi-frame image processing. We've got tracking, and so top middle is single point or multi-point tracking. Top right is region tracking for planar surfaces. So these tools allow an artist to pick out a particular point in the shot, and they have workflows to create modified video that's pretty consistent whatever they're doing. You take a video shot, you track something in it, you stabilize that to one frame of reference so that you can manipulate it. You then match move the change that you made back into the shot. And they, according to the content that they're working with, they might do that different ways. So the hand might be easier with a single point, the back of a wall would be easier with a plane, or anything that's pretty far away from the camera you can treat as planar. So we've got tools that deal with planar tracking. They tend to deal with regions or sparse points. And we also have full frame motion estimation. So these motion estimation algorithms give people the ability to take creative control of the look of a shot. So you can retime the dynamics in it, give it more emphasis, speed something up, make it look like it's fast action, slow it down, change the shutter speed, so that you can really sort of emphasize and change the look and feel of a shot. So this deals with dense motion estimation. In the bottom middle, I don't know if anyone can recognize that movie, I see it straight away now, I spent too long on that shot. It's from the Gatsby. And this is doing dense pixel matching between stereo views in a stereo 3D camera. So this is for manipulation of stereo footage for stereo 3D movies. And actually, so this is a tool that Fred was working on. So I don't know if you mentioned Frederic Besset was an ex-student. So Fred came to us after his PhD. He had done his PhD around stereo estimation. And he came on board to work on a tool set for Nuke that deals with manipulating video footage, and he was given the job of creating a new colour matching tool. So the problem with shooting stereo 3D movies is you've got two big cameras. You tend to shoot through a mirror on one of those cameras, which has a polarising effect. The colours are different, the highlights are different in the two cameras, and you have to be able to copy the colour and appearance from one eye to the other eye so that the world you look at on the movie is consistent. Any differences in highlights or lighting between the eyes leads to strain and fatigue when you're watching the movie. So Fred came along, we gave him the job of creating a colour matcher, and actually everyone in the world is using this now because it's really, really quite good. So that's one of the things that he came on board to do. And the bottom right is all about camera motion understanding in shots. So this is really classic work that happens in compositing. So I've got a little breakdown to illustrate how we use those sorts of tools. So this shot here, it's not a shot breakdown that we did, I've just copied it off the web because it's really quite nice. And the challenge here is to create the look of a winter scene in the footage that was recorded on location. And I'll just talk you through it as we go through the shot. So it wasn't actually winter to begin with, that's the problem. So we've got our shots, comes in, and we do a technical grade to get an equalised look. We then track the camera and estimate sparse points in the scene to help us understand where things are in physical space. We take those points, we mesh them to create projection surfaces. And using those projection surfaces in 3D, we can start to paint in the look with different layers for the different effects for the snow falling in different parts of the scene. And then to complete it, you can add some particle effects and you can create your final look and grade. And this is what you do, going from the footage you shoot on set to getting that final visual effect. So this is just to create the 2D look that you want. And of course, you probably want to go in there and add some special effects, dancing aliens, whatever that you need for the movie. And actually, I was talking earlier about the kind of workflows that 2D artists have and how computer vision can help to accelerate those workflows. And it always comes down to finding a domain to represent your data that lets artists work and manipulate the footage. So in this case, for example, you might think it's simple to make it look snowy. You make it white, you add some sparkly snowflakes, but actually you've got some car tracks that you need to add into the snow afterwards. And the motion of those car tracks have to follow the original footage. The perspective of those car tracks have to move correctly with the camera move. To get that right, you actually need a physical representation of the road in a 3D space so that you can paint those tracks once and then render them back down to the shot. And so artists use a 3D space with simple projection surfaces really quite often. And all of the algorithms in here are kind of really standard computer vision algorithms you probably get taught in the first 6 months of the course in the MSc. Is that right or not? Possibly. Okay, so I wanted to give you a picture of kind of the computer vision tools today or in the past, things that are coming up now, and think a little bit about things in the future. So structure from motion algorithms, projecting things in 3D, very standard now with computer vision in film post-production. And this is a tool that we've been working on, one of the tools we've been working on over the last year that we're about to release with our new product. And this is using dense motion estimation to help artists edit footage quickly and more easily. And this example shows typical things that happen in production. So this is a shot from Power Rangers movie. I don't know if you're going to go and watch it. I don't know if I am. But so this shot on set, they shot the whole take or series of takes, and the actor's suit zipper was open. So the black line across his back was because his zipper popped open. Maybe he was a big guy, I don't know. So they made the call on set that they wouldn't reshoot the whole production just for this guy who hadn't had his zipper done up, because of the impact of the cost of that. It would cost them a huge amount to return around the set, reshoot all that content. It might set them back an entire day, which is a huge cost. So typical, they say, well, we'll fix that in post. So there's some poor artist's job to repaint the whole of that bag section for the whole of the shots with all of the lighting effects that need to go into it. So there are ways that you can solve those problems today, and people solve them all of the time in movies with the different tools that are available. You might be able to take a patch, track different parts of the patch into the shots. You might track a geometric representation of the back over time and then create a texture map that you paint. But what we've done here is use motion estimation to allow an artist just to paint a single frame that they can do once really quickly, and then propagate that change across the remaining frames in the shot. So they paint one frame, and then they can push that over time. So algorithmically, for us, there's all sorts of really interesting, challenging problems there. There's how do you take motion estimation and make it work across a whole shot? How do you do picture building that doesn't degrade or break down or break up or require fixing every frame? It's just got to be correct at every frame. And then how do you present all those algorithms to an artist that gives them an easy way to use it? So it's got to be quick, it's got to be easy, it's got to be responsive. So those are the sort of problems that we deal with. And for example, this would be a 12-month job for one of the R&D engineers to work on. They might spend 6 months working on the algorithmic side. They would connect with one artist working on production for a short period of time to try out the tool, understand how it works in the films that they're working on right now. They would build a prototype tool they'll roll out to a small subset of clients that we have, and that will then lead up to a release, which is happening very soon for this tool. So that's one of the things that we've done recently. And thinking about things coming up in the future, so this is a collaboration we've had with UCL. with Gabriel Borosto, Wenbin and Bath University, and this is looking at the potential for future tools. And the tools that we create are very much about making it easier and faster for artists. And this project was looking at basically one of the bottlenecks in film post-production today, which is rotoscoping. Artists have to take a film footage, they have to go into each frame and break out all of the different elements that are there into layers, so that they can treat each one separately, so they can integrate elements behind different layers, and that takes a lot of time, a lot of effort. A single frame can take several hours to days to work on, and there's a whole industry in India based around it. Film gets produced, gets sent over to India, they rotoscope it, comes back again, might not be correct, gets sent back to India, comes back again, goes backwards and forwards. So it costs a lot of money to go through that process. So this project was looking at putting machine learning into these tools to see if the artist tool can learn the shape that it's working on to make it easier and faster to produce the correct shape. So if I can find the right slot in here. So a roto shape is just a spline with spline handles and controls that you work on, and typically you'd have to change every single point here to get it to the right place. But if you put an understanding of the shape space in there that the machine has learned, machine learning, you can pick up all of the points and you can drag it with one click and drag. So this is really the extreme end of the tools that we produce. We want to take it down to one click, one drag to get to the right place. Then you're much faster in the work that you're doing. And so this is a great example of a collaboration, I think, between an industrial partner and an academic partner. The academic partner understands the algorithms that they're using, they can try it out, we can provide guidance on the tools and workflows that are needed. And in particular for me, one of the important things for this project was to get really realistic industrial use cases into the research problem. So a lot of research is based around almost toy examples, test cases, benchmarks, test scenes, and quite often we find in industry that these test scenes don't really represent the real world. So when you look at the research, you can't really understand how it's going to transfer. And if you try and transfer it, it doesn't always work because it's been designed to work on a lab desk or a very constrained set of data. So one of the things we did working as part of this project is producing a professional database that's been fully rotoscoped that we can make available to the academic community. So that's one of the projects that we've been involved in with UCL. And we're involved in a variety of projects thinking about the future and how things change. And the way movies are being produced is going to change. It's changing already. And Kate was showing the real-time performance capture with motion tracking, and you can see a digital character at the time of shooting. And this is potentially the way filmmaking is going. Instead of being divided between a production stage, everything gets recorded, sent to post-production, then it gets remade, these phases are beginning to be combined in what's being called virtual production. In virtual production, you'll have probably seen case studies around Avatar and The Hobbit. You actually can see on set a live preview of the visual effects that you would get, usually many months later after lots and lots of work. So as soon as filmmaking allows a director to see the visual effects becomes a much more creative process. So we think filmmaking is going to change to be much more of a collaborative, on-set process where you can actually see visual effects at the time of shooting. So we're involved in coordinating an EU-funded project that's looking at things like global illumination running real-time on set, compositing happening in real time on sets, multiple collaborative editing of digital assets with visualization at the time of shooting. These sort of real challenging problems. And this is just one example of one of the outcomes that we've been working on in the project. And what this is supposing is that the data that gets shot in films is going to change in the future. We're collaborating with a company that's doing live slam tracking on set, so you can pick up a camera You can move it anywhere you want, and you can understand where it is and what it's looking at. And they're also recording depth as part of that shoot. So instead of getting colour images from set, we're going to start getting RGB-Z images from set. And once you've got RGB-Z, you don't need rotoscoping anymore because you know the depth in the scene, and you can start to integrate your elements nicely and cleanly in depth. So the reason why I've shown this is that this again came from partly from a collaboration with UCL. So we had an Eng.D student who came to the Foundry, and he was kind of a follow-on to his MSc project, which was looking at in-painting for rig removal, which is also reasoning about depth in the scene. He then moved on to look at image matting algorithms. Matting is the process of understanding the opacity and blur and bleeding between different layers in the scene. So under the hood here, we've got an algorithm that looks and estimates opacity so that you can correctly blend your CG element with your foreground, and understanding where there are depth changes. So part of that work helps with this. And that was an Eng.D student. And then looking at the future of film content. So I didn't realise that VR would be a theme, so I've only got a couple of slides on this. I don't know if it's really interesting or not. But within the film industry, there does certainly seem to be a lot of excitement around creating a new type of medium, if you like. And people are exploring it in different ways. So the examples I've got up here, top left, is exploring the idea of first-person cinema. So this is a war movie recorded with a 360 camera rig, and you can actually put the headset on and you can follow the story as it happens, feeling like a slight once removed from the action as it unfolds, following the story. We see clients working on experiential content. A lot of people are trying horror in 360. It's the first thing you want to try or not want to try. And it's interesting because putting on a 360 headset adds different levels of immersion. You go from watching a screen to having the content all around you. You go from audio which is placed to audio that feels like it surrounds you. And then this experience that they did top right, you actually watch it while strapped to a wheelchair. So you start to get touch in there, and they actually have a butt kicker as well. So as you go along and you're wielding the wheelchair, you get a smack in the arse. So it really kind of grounds you inside that experience as you watch. And a lot of people are trying experiential stuff. We also see people doing co-marketing releases. So you can't really tell, but this is down here on the bottom left is a release from Jurassic World. So when Jurassic World came out, they also had a 360 trailer. Put the headset on, see the dinosaur almost touch your face. You can get excited about the movie and go and watch it. And bottom right, I found particularly interesting. So this is Strictly Come Dancing. I don't know if anyone recognises it or would admit it. So the BBC puts a small form factor 360 camera on set or inside the show for the performance, and they recorded the performance and they choreographed it so that the dancers moved around the camera, and then they released it shortly after the episode. So I think what this shows is the potential for episodic content for 360. So all of these are quite short form factor, we call it, very short experiences, 3 minutes, 5 minutes. So you're not going to be watching a movie with a headset on, but with episodic content, you might start to download the accompanying 360 video. I quite like watching Walking Dead, I don't know why, but maybe after I've watched a Walking Dead episode, I'll download to watch a particularly gory bit the next day, and maybe I'll even start to pay for that type of content. So we are seeing a lot of people starting to shoot this new type of media. I don't know how successful it's going to be in storytelling, but one of the things that I find quite powerful, I mean, one of the things I do see straight away is that there is a new type of journalism that seems to be happening. So worldwide there seems to be a refugee crisis that's unfolding. So a lot of new types of journalism companies are going out to locations and recording in 360 what it's like to be a refugee. And that gives you a level of understanding of what it's like for people in that sort of situation. And this video, I'm not going to play it back, I'm going to skip through it. It's actually, in the same way that the Mummy clip seems to have stuck with me for the last 8 years, I think this is one that's going to stick with me for I don't know, forever. And this is a piece about child abuse. Now, these sort of topics you can read about, you can try and comprehend, but you can never possibly understand what it's like. So this piece tries to, it's educational, tries to explain to you what the situation might be for a young child. And it wasn't really until I put a headset on and saw the loneliness and helplessness of the situation that I actually felt what it might be like to be there or be that person. So I found this really a very powerful story to follow. So I'm not going to show it. If you want to see it, it's called Terre de Homme, and it's by a client of ours called Ambassadors. So I spent a lot of time about VR, and as a computer vision scientist, I find it really interesting because producing VR content has all of the same problems that there are in post-production today. So post-production today, you shoot with a movie camera, you've got to understand the 3D world, you've got to put things in it. If you shoot stereo movies, you sometimes deal with 2 cameras. Well, to shoot 360 movies, you've got many cameras, so it's only going to get harder. And actually, the rig that you see here is one that Framestore put together to shoot a Volvo reality clip, and it was in one of your showreels at the end. So to shoot that, what they wanted was a 360 video panorama of a road scene, and to shoot it, they chopped the top of a car and put together some of the most expensive cameras in the world to get the highest quality 360 video probably that still exists. But there are real challenges to stitch that into a single seamless 360 view of the world, because as we know with our eyes, if you blink, there's parallax shifts, things don't line up. And that's exactly what happens when you've got large cameras with large offset between them. So the problems of dealing with camera orientation, camera geometry, 3D scene understanding, to build a beautiful picture to show to a viewer is exactly the same as all the other compositing problems people face in post-production. So this is kind of a new world, and we're working on a new tool set to deal with 360 video. And that's me. So thank you very much.
First of all, thanks for the talk, and I think Nuke is fantastic, and everyone working in research with images should look into it, as they keep saying to the department. But when you're writing C++ in Nuke, you often get the feeling that it's still very much scanline based, and if you want the whole image, it kind of breaks the computational graph and you slow everything down.
Yes.
And yet a lot of the problems that we work on always require full images, whether that's denoising or structure for motion. So is there any plan on your behalf to change Nuke to deal with that kind of algorithm that needs global information?
So yes, it's not necessarily the best answer in the world. So the way Nuke works on scan lines is historical, because I'll get to answer the question, but it's important. So by dealing with scan lines, you can actually scale up to deal with images at resolutions like 32K. So one of the things we have in our industry is map painting for projection works. You need to produce the most beautiful backdrop of a painted skyline, and you need to render that into your movie, and artists work at resolutions of 32K. And these are resolutions that don't necessarily fit into memory, so you have to deal with small parts of an image at any one time. So that's why it's scanline, and that's why it probably won't change from that anytime soon. But we are introducing tile-based processing, and there are tricks to be able to deal with full frame processing. You can block the thread, you can grab the whole image, you can store, and then you can just feed it back to the rest of the scan lines. So quite happy to help out if anyone wants to do full frame processing in scan lines. But there's also tile-based processing you can get to through the planar image IOP, if you want to.
Thank you.
That's all right. It's good to know that you're using Nuke.
Yeah, always.
Looking at the setup of that rig using the GoPros, or anything else that is, if you want true stereo and multiple true stereo, what you have here is divergent cameras. How do you get the correct effect?
So it's a very interesting question, and I forgot to mention it, but so Google, the cameras here is called the Google Jump Rig, and Google have been working on a piece of technology they're calling the Google Assembler that allows you to record with this rig, upload, and they will stitch close to seamless stereo 360 view. And the way that view is generated is quite involved, but effectively, if you imagine your eyes on a circle, and if you're looking at a panorama, if you take each eye on a circle and swing it around that circle, pivoting in the middle, and you take vertical slices, then you're taking vertical scans out of the real world. If you've got divergent cameras, they are actually sampling the world at the right point to be able to generate those scan lines. It's just that you have to be able to sample correctly from the original camera images to that stereo panoramic view.
Are you also increasing resolution by doing that?
Well, you can never increase those resolution. You can try to, there are algorithms to do it, but you inevitably degrade from the original input footage. So the stereo views that people produce, they tend to be 4K per eye or less across the entire 360, and they're recording, actually I don't know how the resolution they're recording, they're possibly recording each camera at 4K, I'm not certain. But they've got the latitude to be able to go to the output resolution without needing to go up in resolution.
Interesting.
So check out Google Assembler, and actually if you're interested in this, Facebook are also releasing their code to do it too.
So I'm actually currently an MSc student in human-computer interaction, and I'm doing a dissertation with the BBC about 360 videos. And I was wondering, with your VR videos, how do you do transitions? Because there's a problem of, like, you can fade to black, in which case the viewer would kind of be less immersed because of that, that cut. So what kind of current methods do you guys use?
So I deal with a shot-by-shot compositing world. So each of those transitions I care about how you produce the most perfect picture. We don't tend to deal with editorial. And I hear people talking about it, and people don't understand how to do shot transitions for VR. I've tried a few experiences where you just cut, and I find it works. It needs a little bit of a shift, but you feel like you're teleporting, which for me works. I don't know if it works for everyone else. I don't know how else you can do it, really. How do you, maybe you could try and morph the world so that it recreates at the right point. I don't know how you do cuts, but straight cuts seem to work.
Since Nuke is getting stronger and stronger on the 3D side of things, do you ever see it fusing with Modo and Mari and all the other things that you've acquired?
So what we would really like in this world of VR is one all-encompassing editing tool where you've got the 3D modeling inside of 3D environments, you've got the 2D view that you want as an output, and under the hood you've got the node graphs that deal with maybe a non-linear story for VR, a non-linear node graph for a visual effect inside it. This is the ultimate editing and authoring tool. Bringing these pieces of technology to create that together is just like an enormous task. Just creating Nuke in its own takes between 10, 12 developers. It's got a QA team of 5 or 6 people. Modo, there's a team of, let's say, 10 people. Don't quote me on this, I'm not exactly sure. But to create that one authoring tool that brings all those things together, it's a huge, huge task. So we as a company are very interested in connecting the tools so there's a coherent tool chain. It's going to be a long, slow process for us to get there.
Do you see, so there's a lot of know-how and kind of tailoring and industry-specific knowledge that goes into developing lots of these applications, and the new trend in computer vision with deep learning and so on. Do you see some of those techniques kind of replacing some of the human interaction, or how do you see essentially this learning paradigm?
I would really love to know. So all of these tools that we produce here, they kind of feel like computer vision from the last decade. But the reason it works like that, because so these computer vision techniques are model the world, then deal with your model. The reason that works so well is that an artist can have an intuition of what that model is, and you can present control parameters that they can understand. So the artist has to have total and utter control of the result that they get. We've looked at computer vision algorithms for texture synthesis, for example, in the past in painting, computer vision algorithms for tracking by detection, these sort of things that were fashionable, I don't know, 5 years ago. When I looked at it, you don't have control anymore. So I think deep learning could be really exciting. It seems like the world is working on deep learning. Yeah, Fred went to work at DeepMind. The guy who worked on the matting work, he's gone to DeepMind. Everyone's going to DeepMind. But I think they're going to be great if they just work and you take the results and maybe it solves 80% of the problem. That's fine, and then the artist can work on the other 20%. But if they are used, if they don't have any control, they have to work perfectly. Because if it just looks good enough, but you still have to edit every frame, there's no point to begin with. And, yeah, you just wouldn't use it.
I think you already described one really important point where you guys can come in this whole process when you describe the work that you've done for SIGGRAPH this year with UCL and Bath, which is, you've generated lots of data that has annotations. So you can generate data sets for training all these, big deep learning systems. And I think that's where, the power of these methods are actually going to be very, very important. So we use the kind of old traditional computer vision methods that have a generative model to generate all the data. Then we've got annotated data, and then you can train your
It's a huge task, isn't it?
Of course, yeah. But you're kind of working on some different problems now.
Yeah.
Saying, we can generate methods that can generate training data, and then machine learning can learn from that and do a job on data it hasn't seen before. So.
Yeah. And the way I think I'd like to say it is something that can deal with cleaning up or improving what you get.
Yeah.
So, for example, this was really a great result for us because it took our motion estimation technology, this is the stereo disparity to get the two cameras, and it was a big change to algorithms that reasoned over large areas of an image, but to get coherent depth layers in the scene. But as soon as you take your algorithm to that larger scale of problem with large interconnections and large priors, you're slowing it down hugely. So can you take a lightweight algorithm that's not particularly good, and can you have something that runs on top of it, kind of bootstrapping the learning, so that you can get beautiful, clean results out of it fast? That would be fun.
Great. Thank you very much, John. We're running a little bit over time. So Dan's going up as our last speaker. So Dan leads the robotic surgery group at UCL. So they have robots to do laparoscopy surgery, and they're looking at how to extract visual information from cameras to do surgery automatically, which is an incredibly hard problem to solve.
Hopefully.
So obviously they're looking at computer vision, have solutions for looking at laparoscopic images and virtual reality, augmented reality.
Thanks, Lourdes. So this is what I have been doing, but obviously now I'm going to go and work in VFX, because who doesn't want to blow up satellites and do social change and so forth? It's really, really amazing stuff. So the stuff I'm going to talk about really is very similar in some of the fundamental technology, but applied to a completely different domain. So I've tried to reduce the goriness as much as I can, but working in surgery obviously inevitably means that you'll be looking at some images that you may find disturbing. This is actually probably the most disturbing image. So surgery requires instruments. Now these are instruments from a very long time ago, when surgery was in fact. So did you know that surgeons used to be paired up with barbers? So actually, the Guild of Surgeons was joined with the Guild of Barbers, and a lot of surgery was performed by barbers. Right? So the instrumentation used those days was obviously quite crude and cumbersome, but the important point to take home here is that surgical instrumentation is essentially invasive. So you've got this type of scenario where you're going to use clamps and open up the body and try to stick your hands in order to correct something that's not going quite right. Now, I tried to make this look interesting for some reason, and I found this amazing image of somebody having brain surgery while playing the guitar at the same time. Obviously, this was in LA.
This actually happened?
Yes, this actually happened. This is in UCLA. It was an artist who was suffering from essentially onsets of Parkinson's, and so they went in to do deep brain stimulation. So this is where you insert electrodes deep into the brain, and you use electricity to stimulate the brain, and it alleviates some of these effects. So you can do this for epilepsy as well. So being an artist, he played the guitar during surgery. Different people use different techniques to monitor cognitive processes while you're doing a procedure. So surgery is invasive, but luckily for a very long time now, people have been looking at how you could potentially see inside the body without causing lots of trauma and invading it by making large incisions. So this is some early work on the topic in the 1800s in Austria and in Germany. So here people were trying to develop devices to allow you to see in the stomach. Okay, so you can potentially enter through the esophagus and you don't make any incisions, and then you can see what's going on, what sort of illness the person might have. So the problem was that they have to deliver light, and at the time they didn't have LEDs and fancy, electrical ways of doing this. So you deliver light using a candle, and then you have a rigid rod where you want to insert it to see the stomach. And they managed this. They had one problem, and that was that they had to use a very, very specific patient group. Can anyone guess what the patient group was?
Sword swallowers?
Exactly, yes. So basically, they tested this, but the only person that could do it was a sword swallower. You can see this guidance on how you insert the tube. Anyway, luckily, things have changed quite a lot, and so nowadays you've got very, very small CMOS technology. You've all got it in your mobile phones. You can mount this at the tip of flexible instruments, and you can basically see inside the body with very, very small incisions, so you don't put your hands in. You've even got devices like this, so we actually have a project on building a robotic